Hi everybody, I'm Dermot O'Shea, host of the Antenna podcast, and today I'm delighted to be with Jaime Molins Benlliure. Did I say that correctly?
Yeah, really correct. Yeah.
Very good. Would you like to introduce yourself maybe and tell us a little bit more about yourself and your career today?
Okay. So yeah, thanks for inviting me to the podcast. It's, to be honest, the first time I'm in a podcast. I'm really glad to be in here. Yeah. My name is Jaime Molins Benlliure, like the second name in Spain. I'm an antenna engineer, so I've been focused working on small antennas. I started studying at the University Polytechnic of Valencia, and then after doing some 4 years of research, I joined Taoglas as an antenna and RF engineer.
Okay,
so, yeah.
And we're here today at the EUCAP, which is the European Conference for Antennas and Propagation,
Yep.
which you've been very, very involved with, right, over the years?
Yeah, I think this is the fourth time I'm in here. I did 3 conferences when I was in my PhD program, and then this is the first time I come with Taoglas. So I think we are getting benefit a lot of coming in here. We are getting a lot of interaction with students, with professors, and with some other companies. So it's a great opportunity also for them to get us know.
And you have a talk on here yourself at
Yeah.
the conference. What's the subject?
So it's about low power wide area networks, and I have designed an antenna for that.
Okay.
So it's a really miniaturized antenna. It's a 30 by 10 by 5 millimeters antenna. It is working at 433 megahertz, which is quite low frequency.
Yeah,
antenna.
that's very challenging to do a small
That's
antenna.
our main challenge in our company and our antenna, small antennas issue, like to integrate such a small antenna due to its wavelength is really challenging.
Yeah, maybe explain that to people. Why is it difficult to make a physically small antenna at a lower frequency?
Yeah, it depends on the frequency and the wavelength. So the lower you go in frequency, the bigger is the wavelength. So you need to have a resonant antenna. So a minimum resonant antenna should be lambda over 4. So let's say at 433 megahertz, lambda over 4, it's about 17 centimeters.
Okay.
So you can imagine how you can fit a 17 centimeter antenna in a small device, IoT device. So for these low power wide area networks, they are for long distance communication and for IoT. So you know that these devices are limited in terms of capacity. They are limited in terms of antennas. They have since they are smaller, they have lower efficiency. So it's quite challenging to have a connection in such a long range, but they can get the benefit of working at a lower frequency. And we go back to what we were explaining about, like the lower you go in frequency, the bigger are the antenna due to the wavelength they have.
Yeah.
So we kind of achieve of miniaturizing an antenna that should be 17 centimeters, and we have applied multiple miniaturization techniques. We are using ceramics, which generally we use. It is called material loading. Okay. So if you have ceramics, they have electrical high permittivities, and what you can get from them is, since they have a high permittivity, you can load. It is called loading the antenna with a material. So an antenna can be miniaturized by adding this kind of materials. Okay. So this is one way we miniaturize the antenna. Second way we miniaturize is adding meanders, which is bending the antenna, but you have to be really careful, because if you do too many meanders, what you do is like you can kind of counter the currents and do current cancellation and mismatching effects, so you are dropping the efficiency. So it's always when we were talking about small antennas, it's always a balance in between size and performance.
Yeah, so it's not just about I can meander the antenna, fold it up, scrunch it.
You have to be really careful. So there are some techniques that you need to avoid, but we are always constrained about size. It's always about the size of the device and how, like the space you have to place your antenna. There's some, like a lot of theory beneath. There are the Chu and Wheeler limits that they say if you are kind of enclosuring an antenna, you have it is set by theory the maximum bandwidth you can achieve. And every time you make that area or that volume smaller, you have to pay in terms of efficiency and in terms of bandwidth.
Okay.
And there's no other way you can go for a smaller antenna. I mean, but that's the limit. There's a huge range depending on how you miniaturize the antenna, that you will get more losses or less losses, but you have always a limit, which is a theoretical limit that we all know.
Yeah, there's laws of physics, and you can't cheat the laws of physics. Yeah.
Yeah, eventually it's good to have this kind of low knowledge, because in this market there are many companies, and they you can kind of see a design and you can try to replicate, and it is easy to say if you create a meander you can make an antenna smaller, but there's a lot of study and a lot of research on how to do it properly and how to shrink antennas and having high efficiency.
Yeah.
So we are having an efficiency at about 38% with that antenna. And also another topic I would like to introduce, and it's good to know, when you have such a small antenna, you have to get benefit of the radiation you get from the PCB. So all the integrable antennas, as an engineer, you have to think the antenna is kind of a matching element, and what is radiating is the PCB.
Okay.
But you have
to
create.
This is you mean the main PCB of the device is becoming your antenna basically.
Exactly. So you have to think like your antenna is a matching circuit that it is exciting the modes of the PCB, like the natural resonance of your PCB, and that way you will enhance the performance of your antenna. And
does that mean you have to work closely then with the customer designer of their PCB?
Obviously, from the beginning, we have to talk. It is really important to have contact with the customers, because it's really important the placement and the size, the placement of the antenna and the size of the PCB where you are installing the antenna. It makes such a big difference, and especially there are two kinds of antennas, depending on their nature. There are capacitive coupling elements or inductive coupling elements. So to explain it simple, a capacitive coupling element will be like a monopole-like antenna, and an inductive coupling element will be like a loop.
Okay.
So you can go around and see, sometimes people ask us, you sometimes say that it is better to install a small antenna in the corner, and some other papers say, or some other datasheets say it is better to place it in the middle of a site. And why is that? Are you lying? Or, no, I mean, really depending on the nature of the antenna, it is better either to place it on top or the corner or in the middle of the site.
Okay.
And that can bring us to the topic of how I kind of started about my research. I was focused on studying the characteristic modes of any metallic objects. So the theory of characteristic modes, like it was like studied or presented long ago in the 50s, 60s, but since kind of 30 years ago or 20 years ago, my previous research group, the Antennas and Propagation Lab from the Polytechnical University of Valencia, they started to use that kind of niche theory to design some like daily antennas that we know, like PFAS, monopoles and stuff like that. And since then, they started to kind of show to the world that it is possible to design antennas with that theory, the theory of characteristic modes. So the goal in here is, without exciting anything, is you have an structure and you are analyzing its natural resonances.
Okay. So any part of the device, from the battery to the screen to
but mainly talking about metallic objects in order to excite them and make them radiate. You can either analyze an antenna that way, or in our case, which is the best, is you can only analyze the PCB, which is eventually in comparison to the antenna, is way bigger, and obviously, since it is bigger, you will have more radiation capabilities.
Okay.
So you can analyze. I will be showing that on tomorrow's presentation. So it is the best is you analyze the PCB. You see the natural resonances of the PCB, and you see where they resonate and what is how easy are they to excite, and the power and bandwidth they have. Okay. So by analyzing that, it gives you like really good hints on where you have to place your antenna.
So but are you also, does that also give you, okay, so putting it in the corner or the middle is not always maybe the best position, because when you look at the antenna spec, it'll always tell you exactly where to place the antenna.
Yeah.
Are you saying then, but based on the characteristics of your PCB, that may not be the case? You may need to place it.
Yeah, but at the same time, depending on the characteristic of your PCB, you will have different, let's say, current distributions, and then you can either feed them depending on the mode you wanna excite. You can pick different kind of antennas, but with the two different kind of antenna with either inductive coupling elements antennas or capacitive coupling elements antenna. With the two of them, you can excite these modes. But the customer could come to us and say, look, I cannot place the antenna in there. So we can think about another antenna with different nature to place it in another, for example, in the side, in the center of the side. Or if they cannot place it in there, we can go to the top and look for an antenna with the proper nature to excite those modes. So we have that freedom.
Which nature has this antenna, this 433 megahertz antenna?
It's a capacitive coupling element antenna, so that's why we have to place it in the corner. Or top. Okay. So we're exciting the fundamental mode. They have the capacitive coupling antennas. They have to be placed on a minimum of current. So you have a current distribution, and then you will see there's a change in the fields, or in these terms the current. There's kind of a maximum and minimums, and for our capacitive coupling element antenna, we have to place it in the minimum. So we did the characteristic modes analysis, and we were interested on exciting the first mode, which is the one which has more capabilities since it is resonating at the lowest frequency. Okay. So that's our target, and also it has. You can check how your radiation pattern will look like. So we are really interested, since we are an IoT company, and the solution will be kind of a device that we don't know where it will be placed. So we will need an omnidirectional radiation pattern. So the first mode, it has a dipole-like, donut-like radiation pattern, and that's the radiation pattern we need. Okay.
So you know those in advance before you start the design. And when you approach a design, do you use simulation a lot, or do you more use like actual physical antenna design, iteration and testing?
We do both. I mean, it's good depending. It really depends on the solution. If it's a solution for kind of really novel stuff, we generally start from scratch. We have a lot of background about theoretical and like canonical antennas. What I generally suggest, to be honest, is, since the best way of learning is starting from simple things. So I generally start with dipoles, monopoles, inverted Ls, antenna, inverted F antennas. These kind of antennas, we all know how they work. So the best is to start with them and see how they work in the environment you are being exposed, because the environment is playing a big role also always. We are not like in a really easy world that
so
you can
mean
just...
the device environment.
Yeah, that's something really important. So we start from early simulation to see how it's the environment, the impact of the environment in canonical antennas that we already know how they work, the efficiency they generally show, and we see the impact that the environment has. And then it's extremely important, in parallel to do these early simulations, to go to the lab, hands-on, and see the real performance, because sometimes the simulations, they are accurate when the environment is not that complex, but when the environment is so complex, first of all, you cannot simulate and mesh such a complex environment. It will take hours, days of simulating such an environment, so you have to simplify it. So the simplifications comes with some mismatching from what you are simulating to what you are measuring. So you always have to be hands-on and install the antenna in the environment and see if what you have simulated, it's correlating what you are measuring. You are always surprised how many new issues or new problems you are facing when you are installing the antenna, because there are many effects that cannot be taken sometimes into account when you are simulating.
Yeah, and how did you get into this? Like, you're obviously, you mentioned the University Polytechnic Valencia. Did you start there as an engineer, or how did you get into the whole area? Yeah,
to be honest, I did my degree in, we call it in Spain, telecommunication engineering. I started in there. I spent 4 years doing my bachelor's. Then I continued with my master degree for 2 years. And then on my last year, I've been always kind of interested about topics like antennas and microwaves, since I think they were the most challenging and more difficult subjects I was exposed to.
You came across it in university, or
at university?
Yeah, okay.
At university, and then I got the opportunity to do my master's thesis with the research center I was talking about, with the antennas and propagation lab. And then I met Miguel Ferrando, who was my advisor in that master.
Yeah.
So since then, I was starting simulating easy kind of antennas, but we start to build up and create or research about modeling multiple kind of small antennas, focus on small antennas, and also they were also working with some customers. We're doing some small-scale custom solutions, and then I learned a lot about how to miniaturize properly antennas from a kind of a research and theoretical perspective. And then I got this kind of knowledge from them. And when I finished my kind of my thesis, my master thesis, then they proposed me to stay in their laboratory and do a PhD program. The PhD program was focused on the design of small antennas to analyze them with characteristic modes.
Okay.
So then I work with Miguel Ferrando and Evan Tonino and Marc Tacavedo, who are also really involved in the small antenna topics, and especially in characteristic modes.
Okay. And so the characteristic modes, maybe we can finish by talking more about that, because I often hear about, is this related to, I often hear when we're working on projects from either customer engineers or engineers in Taoglas that, the connector was acting like an antenna, or the capacitor was acting like an antenna, or some other component on the board was acting like an antenna and causing problems, right? Is this where the characteristic modes come into place, or is it a different
I will
topic?
say it's we generally use it in advance. I think it's better to use it kind of using as a reference in order to afterwards use it to place the antenna properly. Okay. So it's good for a previous reference. Then after, for checking this kind of issues, it will be more difficult, since probably they are kind of higher order or higher frequency issues.
Okay.
And they are all meant, it is better to to use them in some canonical shape and more not so complex environment, because you will suddenly see so many modes that you lose kind of the concept. You will not understand. There are many modes and you don't get which mode is radiating. Also, you need simulations which are really heavy, and if there are some issues on the simulation, you can kind of lose the topic. So I think they are extremely good as a starting point, especially when we have kind of off-the-shelf products that we are constantly designing from scratch in order to beat our competitors in terms of performance. And I use them a lot in terms of when, for example, we have kind of internal projects that we tell us we have this size of a PCB and we need to have an antenna integrated for this frequency band. So the starting point will be analyzing the PCB with characteristic modes in order to see what the performance will look like and what will be the best nature of the antenna, or which antenna nature you should pick. About the capacitive coupling element or inductive coupling element we were talking about previously.
Yeah. Okay. No, it's more great examples of why we can't underestimate the complexity of antenna choice, definitely. Integration, and implementation. Right. So it's critically important. Any advice for people that are interested and would like to get into this industry or get to know more about antennas?
Oh yeah, definitely. I mean, eventually I think it's a really nice environment, and you get to know a lot of great people and great professionals in this kind of area. The best advice I could do is focus first on learning the theory. That's something I think it's really important, and some people in let's say in the industry sometimes don't pay attention, and sometimes like focus on theory first is the best way in order to counter some effects in future that could be solved in half an hour, that sometimes they are solved in days, because you don't have enough kind of theory knowledge to kind of counter them. But yeah, the best is to focus on theory, and then it's at the same time something that you shouldn't focus only theory, and then learning the theory, and then after moving to kind of hands-on and laboratory stuff, which is also really important. As a former researcher, it's something I was missing. Even finishing my PhD, I was lacking some hands-on on the laboratory, since obviously the laboratories are places with really expensive stuff, so you don't have really easy access to them. But eventually, when what you see in simulation is not necessarily 100% that what you will see when you fabricate the antenna, and it's really important that as an engineer you know in advance what kind of issues you will be facing. Yeah. Because you could find some surprises or some issues, especially by adding connectors, by adding cables, by adding matching elements that could not work the same way they are working in the simulators. There are many effects that you should take into account. Also calibrating everything in order to have proper response. So there are many things that they are in parallel, they are aligned, and we have to keep an eye always on theory, but at the same time also on integration and laboratory tasks, which are also really important.
Gotcha. Yeah, I suppose, because I always talk about, engineers, good antenna engineers have great creativity and a lot of experience. That's what makes them great antenna engineers. But what I'm hearing from you is you need discipline as well.
Oh yeah, definitely.
Like the calibration, for example. A lot of people don't want to do that.
No,
because it's boring, repetitive, but it's very important. So you need discipline also.
I think as an engineer, you have to be like really disciplined in terms of you have to follow steps. You cannot cut corners. Especially if you cut corners, sometimes you can give away efficiency and bandwidth, what we were talking about. So it's really important that you are systematic. Otherwise, you can get results and you don't get benefit of them. So you have to be systematic in terms to be efficient and in terms to learn, because you could see some results that could be interesting, but if you are not systematic, you could be missing the information that it's given to you by the measurements you are doing. But yeah.
Okay, well that's great. Listen, we could talk about this all day, and I'm delighted that we have people like you and Taoglas that can have the discipline and the creativity, because it's hard to have it, that's for sure. So thanks very much, Jaime.
No problem at all. It was a pleasure to come here.
Yeah, I'm Dermot O'Shea, host of the Antenna podcast, and thanks for listening to another episode.
Thank you.